students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as ray optics. We're going to do the numericals of ray optics today. Let's see this. Take down the sum please. A glass sphere has a radius of 6 centimeters. A glass sphere has a radius of 6 centimeters and an air bubble is trapped in it. And an air bubble is trapped in it. A glass sphere has a radius of 6 centimeters and an air bubble is trapped in it at a distance of 1 centimeter from the center. At the distance of 1 centimeter from the center. A glass sphere has a radius of 6 centimeters and an air bubble is trapped in it at a distance of 1 centimeter from the center. Determine the apparent position of the bubble. Determine the apparent position of the bubble when viewed from. Determine the apparent position of the bubble when viewed from. First part of the question, nearest surface. Second part of the question, furthest surface. If the refractive index is 1.5. If the refractive index is 1.5 from the nearest surface, furthest surface, if the refractive index is 1.5. Right? First, let's try to understand the diagram. There will be two parts to the diagram. Let's see observation from the nearest surface. Observation from nearest surface. Right? You have a glass, you have a sphere. A glass sphere has a radius of 6 centimeters. Right? This is the center and this is P. So this distance is going to be my radius. From here to here is going to be my radius. An air bubble is trapped at a distance of 1 centimeter from the center. So that means here is where my air bubble is going to be. So let's assume my air bubble is at a point O. Now it is at a distance of 1 centimeter from the center. If it is at a distance of 1 centimeter from the center and if I am looking at it from here, my eye is outside the sphere, that means the distance of the object from the sphere U is going to be 5 centimeters. So I can say radius. Now radius is going to be minus 6 centimeter as per sign convention because the sphere is being drawn from the left hand side, nearest surface. Right? Anything that is to the left is negative, anything that's to the right is positive. U is always negative, so U is going to be minus 5 centimeters. Do we understand how 5 centimeters? Radius is 6 centimeters, 1 centimeter away from the center. So between the surface of the sphere and this object is going to be at a distance of 5 centimeters. Right? Now, for the refraction of spherical surface, you have the formula that mu1 upon u minus mu2 upon v is mu1 minus mu2 upon r. This is my spherical surface formula, right? Now, mu1, refractive index of glass, is 1.5. U is minus 5 centimeters. Mu2, where's my eye? Eye is in air. Refractive index of air is 1 upon V is 1.5 minus 1 upon R. Radius is given to you as minus 6. Right? So you will get this as minus 3 upon 10 minus 1 upon V is nothing but minus 1 upon 12. So in that case I will get minus 3 upon 10 plus 1 upon 12 is 1 upon V. So in that case you will get this as 1 upon V is nothing but 13 upon 60 if I take LCM. So therefore I can say V is nothing but minus 13 upon 60. So V is minus 60 upon 13. So that's minus 4.615 centimeter. So the image of the bubble is going to be observed at a distance of 4.615 centimeter, minus 4.615 centimeter. That means the bubble will appear 4.615 centimeters below the surface of the sphere. Negative side below the surface of the sphere. The bubble will appear 4.615 centimeter below the surface of the sphere. That's the first part of the question. The second part of the question. Observation from the furthest surface. Observation from furthest surface. Observation from furthest surface. Now, if I want to observe the sphere from the furthest surface, that means let's draw the diagram again. This is your principal axis, center, furthest surface, that means the bubble is going to be on the other side of the center. So this is where the bubble is going to be. Okay. This distance, let's call the center as O and C. This distance is R and this distance is 1 centimeter. Therefore, U, this distance is going to be U. So, I am viewing the bubble from the furthest surface. The eye is here. Right? So, in that case, U is going to be 7 centimeter. By sign convention, we know that U is always negative. Radius is going to be minus 6 centimeters because I will have to keep the center on the left side to draw the spherical surface. We also know that mu1 is 1.5 centimeter and mu2 is 1. Again, use spherical surface formula and solve it. You already have spherical surface formula. I have already shown you one part of it. Same formula you will use. Mu1 upon U minus mu2 upon V is mu1 minus mu2 upon R. Guys, I am not solving it. I have already solved one part and shown it to you. You have all the values, basic substitution, and you should be able to get the answer for this. I am just directly going to give you the answer. I want you to solve this on your own. The answer for this should be minus 7.636 centimeters. That means the bubble will appear 7.636 centimeters below the surface of the sphere. The bubble will appear 7.636 centimeters below surface of sphere. Below surface of sphere. Right? So that is going to be the answer for this. Next, let's see the next sum, guys. Take on next sum. A biconvex lens has radii of curvature of two faces. Has radii of curvature of two faces. Has radii of curvature of two faces. 0.1 meter and 0.12 meter. A biconvex lens has radii of curvature of two faces. A biconvex lens has radii of curvature of two faces, 0.1 centimeter and 0.1 meter and 0.12 meter. If the focal length of the lens is 0.1 meter, if the focal length of the lens is 0.1 meter, find first part of the question, the refractive index. First part of the question, the refractive index. Second part of the question, power of the lens. Second part of the question, power of the lens. Third part of the question, the nature and position of the image. The nature and position of the image if an object is placed at a distance of 6 centimeters from the lens. If an object is placed at a distance of 6 centimeters from the lens. Right? They give you the two data of curvature. I have converted from meters to centimeter. Focal length is given, u is given. First of all, I will use Lensmaker's equation. If I use Lensmaker's equation says that 1 upon f is mu minus 1 upon r1 plus 1 upon r2. You know r1, you know r2, you know f. You should be able to get the value of u. Guys, I am not substituting. You should be able to get, once you substitute here, you should get the answer of mu as 1.545. Right? I want you to do the calculation on your own. I am going to give you the data and the formula. Calculation you should be able to do on your own. Right? That's the first part of the question. Refractive index. Second, they've asked you to find out the power of the lens. Power of the lens is nothing but 1 upon focal length in meters. Right? 1 upon focal length in meters is 0.1. So power of the lens is going to be 10 diopters. That's the unit. That's the second part of the question. Third part of the question, you have to find the nature and position of the image. You can use convex lens formula. 1 upon v minus 1 upon u is equal to 1 upon f. U, you know, is negative. F is positive. You should be able to get the answer for this. The answer for this should be v is 15 minus 15 centimeters. Right? Now, that means what kind of an image is it going to be? The image is 15 centimeters from the lens. Since it is minus, that means it is on the same side of the lens. It is an erect, magnified and virtual image. The image is at a distance of 15 centimeters from the lens, right, and on the same side of the lens as the object. On the same side of the lens as the object, right? Hence, I can say that the image is erect, virtual and magnified. Right? So that is going to be the answer for that. Next, take our next question, please. An object of height 0.1 meters, an object of height 0.1 meters is placed at a distance of 0.15 meters from a convex lens. Is placed at a distance of 0.15 meters from a convex lens. An object of height 0.1 meters is placed at a distance of 0.15 meters from a convex lens. Having focal length 0.1 meter. Having focal length 0.1 meter. Find the nature, position and the size of the image. Find the nature, position and the size of the image. Find the nature, position and size of the image. So I can use the formula of 1 upon v minus 1 upon u is equal to 1 upon f. Right? So I know the value of u, I know the value of f, I should be able to get the value of v. The answer for v should be answer for V should be 30 centimeters. So therefore I can say, now as V is positive, that means this is going to be a real inverted height of the object is not there. It's going to be a real and inverted image, and V is positive. Therefore, it is a real and inverted image at a distance of 30 centimeters from the lens. So now the next thing I need to find out is that is it a magnified or a diminished image. I can use the formula V upon U is nothing but H2 upon H1. H1 is given to me as 10 centimeters. V I just found out, U I know, right? So straight away 30 upon 15 is H1. 10 upon H1 is 10. H2 upon 10. So I'll therefore get H2 is 30 into 10 upon 15. So 20 centimeters. Height of the object was 10 centimeters. Height of the image is 20 centimeters. That means the image is magnified. So magnified, real, inverted and a magnified image, right, at a distance of 30 centimeters from the lens. Next, take down next one please. Take down next one please. A convex lens has a focal length. A convex lens has a focal length. A convex lens has a focal length of 0.15 meters. A convex lens has a focal length of 0.15 meter. At what distance an object should be placed? At what distance an object should be placed from the lens? At what distance an object should be placed from the lens so as to obtain an image, whose size is, whose size is 3 times the size of the object. Whose size is 3 times the size of the object. Right? Now here you could have 2 types of images. If there is a real image form, condition A, when real image is formed, it is inverted. So in that case magnification will be -3. Magnification is given by the formula V upon U. Therefore I can say that -3 is V upon U. Therefore V is -3U. Then I can use the convex lens formula. 1 upon V minus 1 upon U is 1 upon F. Right? So here I will get 1 upon -3U minus 1 upon U is 1 upon 15. Right? Now I could take -3U as a common denominator, or I could just take 3U as a common denominator. So this is going to be minus sign goes up, -1, and this is -3 is 1 upon 15. So -4 upon 3U is 1 upon 15. -4 into 15 upon 3 is U. So U is -20 centimeters. Right? Hence an object should be placed. Object should be placed at a distance of 20 centimeters. 20 centimeters in front of the lens. right? So that was when a real image is formed. What if a virtual image is formed? Condition B, when virtual image is formed, right? When virtual image is formed, it is going to be an erect image. That means magnification is going to be +3, right? Then exactly the same method that we did in the previous case, m is equal to v upon u. Use this formula, then use the formula 1 upon v minus 1 upon u is 1 upon f. Exactly the same way like you solved case 1, and you should get the answer as, I'm not solving this, I want you to solve this on your own. Answer should be 10 centimeters, right? Next, take our next one please. The focal length of a magnifying glass, the focal length of a magnifying glass is 10 centimeters. The focal length of a magnifying glass is 10 centimeters. If a person whose least distance of distinct vision, if a person whose least distance of distinct vision is 25 centimeter uses this glass, find the maximum magnification possible. Find the maximum magnification possible. Now, I want maximum magnification. When will I get maximum magnification? When the image is formed at DDV. When the image is formed at DDV, the magnification is maximum. He's using a single glass, that means it's going to work like a simple microscope. Magnification is maximum. We've done this in one of our previous lectures, right? So I can therefore say that for a simple microscope, maximum magnification is 1 plus d upon f. D is given to you, f is given to you, you should be able to get the answer. The answer for this should be 3.5. It will not have a unit because it is a ratio. Next, take on next one please. Two lenses of power 1.5 diopter and 2.5 minus 2.5 diopter. Two lenses of powers 1.5 diopter and minus 2.5 diopter are combined to form a lens. Determine the focal length of the combination. Determine the focal length of the combination and comment on the nature. Right? They've given you two lenses. I can say that the power of combination, P is going to be nothing but P1 plus P2, which is going to be nothing but P1, 1.5 minus 2.5, so that is going to be minus 1 diopter, right? If this is the power of the lens, we know that focal length is 1 upon power 1 upon minus 1, which is minus 1 meter. If the focal length is negative, then it is going to be a concave lens, it is going to be a diverging lens. The lens combination is diverging. In simple language, concave. Because we know that for a convex lens, f is positive, right? Is diverging as focal length is negative, right? Take on next one please. For a compound microscope, the eyepiece and the objective, have a focal length. The eyepiece and the objective have a focal length of 20 centimeters and 5 centimeters. The eyepiece and the objective have a focal length of 20 centimeters and 5 centimeters. The final image is formed. At a distance of 25 centimeters from the eyepiece. The final image is formed at a distance of 25 centimeters from the eyepiece. Right? If the object is at 6 centimeters, if the object is placed at 6 centimeters, if the object is placed at 6 centimeters from the objective, find the magnification produced. Right? Now, first of all, I can work with the objective. I can say 1 upon V0 minus 1 upon U0 is 1 upon F0. This is for the objective. So I can say that 1 upon V0 minus 1 upon 6. Now, minus into minus is 1 upon F0, 5 centimeters. So in that case, I will have this as 1 upon V0 is 1 upon 5 minus 1 upon 6. 1 upon V is 6 minus 5 upon 30. V is 30 centimeters. Right? So I will get V0 to be 30 centimeters. Right? So what will be the magnification of the objective? Magnification of the objective is nothing but V0 upon U0. V0 is 30. U0 is 6 minus 6. So this is going to be minus 5. Virtual image is going to be produced. This is the magnification that will be produced by the objective. Now magnification produced by the eyepiece. The eyepiece in a compound microscope works like a simple microscope. So that is going to be 1 plus D upon Fe. Right? D we know by heart is 25 centimeters. Fe is given to you as 20 centimeters. So when you solve this, this is going to be nothing but 2.25. Right? Therefore, what will be the total magnification? Total magnification from compound microscope, we know total magnification is the product of the magnification of the objective and the eyepiece. Right? So this is going to be nothing but minus 5 into 2.25. That's minus 11.25. That will be the total magnification that will be produced by the compound microscope. Next, take down another sum, guys. Take down another sum. The focal length of a magnifying glass, is 10 centimeters. The focal length of a magnifying glass is 10 centimeters. What is the maximum magnification possible? What is the maximum magnification possible when a person whose distance of distinct vision is 25 centimeters is using the glass? Single glass, that means it will work like a simple microscope, right? Now maximum magnification is possible when image at VDV, for which the case is m is equal to 1 plus d upon f. So I can say that m is equal to 1 plus d upon f. I know d, I know f. I should be able to get the answer for this. The answer for this sum should be 3.5. Next, take on next sum please. The length of an astronomical telescope, the length of an astronomical telescope in normal adjustment, the length of an astronomical telescope in normal adjustment is 5.1 meters, is 5.1 meters. The length of a telescope length of an astronomical telescope in normal adjustment is 5.1 meters. If the magnification produced is 50, find the focal length of the objective and the eyepiece. Find the focal length of the objective and the eyepiece. Now, for an astronomical telescope, magnification is f0 upon fe. So 50 is f0 upon fe. So f0 is 50 times fe, but they've given me that f0 plus fe is 5.1, right? So therefore I can say f0, 50 times fe plus fe is 5.1, 51 fe is 5.1, fe will be nothing but 0.1 meter. So the focal length of the eyepiece is 0.1 meter. I can say substitute in f0 plus fe is 5.1 meter. So I'll get f0 is 5 meters. Focal length of the objective is 5 meters. That's what we want to find out. Next, take on next one please. A Galilean telescope, Galileo, a Galilean telescope has an objective of focal length, 1.5 meters. A Galilean telescope has an objective of focal length 1.5 meters, and the eyepiece has a focal length, and the eyepiece has a focal length of 3 centimeters. Has a focal length of 3 centimeters. Find the magnifying power. Find the magnifying power and the length of the telescope. Find the magnifying power and the length of the telescope. Magnifying power, how come both are at 0? A Galilean telescope has an objective and the eyepiece. The second one is the eyepiece, okay, right? Magnifying power is f0 upon fe. f0 is 1.5 upon fe, 0.03. So this is going to be 50. It is going to produce a magnification which is 50 times. Now, for an astronomical telescope, the length of the telescope is f0 plus fe. For a Galilean telescope, the length of the telescope is f0 minus fe. Is f0 minus fe, right? So in that case, this is going to be nothing but 1.5 minus 0.03. So that is 1.47 meters, right? this finishes this chapter. We'll stop this here for the day. Thank you very much.